So am I audible?
Yes, sir.
Okay. Okay. So I'd like to make a quick visit on whatever we have defined yesterday. That is the notion of covering space. That means so if you have a map, suppose P be a map from some space E to some another space B, and if it is a continuous surjection, and so assuming this, we can say that if it happens to be true for every, so if you take any point from the space B, if this point has a neighborhood U that is evenly covered by small p, and if it happens to be true for every point of B, then you can say that, so then that E is called a covering space of B, where whereas P is called a covering map. So we would like to denote this E by, so denote the covering space of B by this pair V tilde small p. So whenever I am referring to covering space of some space with this notation, that means this P is a covering map from B tilde to B, and B tilde is its covering space. Okay. Right. And after defining this covering space of some topological space B by means of covering map, you will at once have some facts that for each B, that P inverse B, so that is going to be a subspace of that covering space, and this is a discrete space. Why it is so? Because if you look at this diagram, suppose this is your B, and let us take any B here, small b, and so it has a neighborhood U. So that means so this is your covering space B tilde, where you find out some size slices of this. Sorry. So by means of this, so these are all slices with respect to that P, right? That means P restricted to all these sets, P alpha is a homeomorphism. And on each slices, on each slice, you will have some point here, here, and if you want to take another one, so here. So these points will be collapsed down to this B. Okay. So in each slice, you will get a member of P inverse B. Okay. Because this is a homeomorphism. This is one function. This is a, so because of that reason, you will get in each slice, you will get exactly 1 point. Okay. Okay, great. Another interesting feature that a covering map will enjoy is that P must be an open map. This will be left as an exercise. It's a very easy exercise, but it is interesting. Okay. Just using the definition of covering space and covering map, you will get that result. Yeah. Great. Another fact is that let me just okay, yeah, okay. So before going to some other observations, let me have a look on some examples, on some important examples. We have already encountered a very interesting one, which is so let me just call it example 1. What is that? We have already defined this map from R to S1 by means of this definition. Okay. And this has been proved to be, this is a covering map, right? So if you take any part of that circle, that means suppose you take some part of that circle, yeah, this one. Suppose the angle between these two segments is alpha, and suppose it is theta. That means you are looking around those real numbers t, satisfying that in general 2n pi minus theta less than 2 pi t less than 2n pi plus alpha. Okay. So that means that is what does it give? So n minus this is n plus this, right? Okay, great. So using this, so that means so if you take this, so this is your U. So this P inverse U can be written as a disjoint union of open sets Vn, where Vn's are open intervals n minus theta by 2 pi n plus alpha by 2 pi, right? So generally speaking, if you take any U of this kind, this can be written as union of Vn. And if you are using the same arguments that has been used for that U, that means where it is this t varies along minus pi by 2 to pi by 2. So using that argument, you can always say that this restriction is a homeomorphism. Okay. Right. And since it is a compact space, so this will have a finitely many open sets which will cover that space, right? So therefore, if you take any point, you can always have some kind of U here, okay, which will be evenly covered by P. So therefore, it is a covering map. Okay. Great. Another particular kind of example that can be placed here is that suppose you take any space, you will get a covering map. What is that? Suppose you take any space, okay, then the identity map on X will always be a covering map. That means a space is a covering space of itself with respect to that covering map identity, right? Great. Another interesting one, suppose you take any space X and you are going to take some level of that space X. That means suppose you take 1, 2, yeah. So then you can define a map here by this rule. That means you are taking some X here and take some K here. So this Px comma K must be mapped to X. Okay. So suddenly you can check that this is a covering map. Okay. So for each point of X, this is a map from, suppose let us call it X tilde. So X tilde to X. So if you take any point from X, so you are getting finally many levels, right? That means X cross 1, X cross 2, X cross n. So for each point, suppose you take any B, so it will have the neighborhood X itself. So that P inverse X must be union of this one. You can check. And certainly, if you look at this space, so this is obviously homeomorphic to X via P. Okay. Great. Another example would be, suppose you take number 4, right? So suppose you take a plane and a right circular cylinder infinite cylinder. That means suppose X is okay, and you want to take this a plane, okay. Then this X tilde can be the points of X tilde can be equipped with some coordinates using, suppose let us, so suppose this is a plain paper, okay, and we are taking a right circular cylinder here. Okay. It is an infinite cylinder, so I'm just taking this part. Okay. Okay, great. So then, so this plane can be equipped with coordinates. Suppose let us call it u comma v. Okay. So for any point q equals to u comma v, I'm just giving a definition here that this will be mapped to that right circular cylinder by means of cos u, sin u, phi. Okay. So yeah. So this is a map. So this P is from this x tilde to x, which is defined in this way. That is P of uv goes to cos u, sin u, phi. This is u. Sorry. Okay. Now what can be done? Now let us take a strip around this zero coordinate. Okay. So suppose let us take minus pi to pi. Okay. I'm just taking this strip. Okay. And giving any particular v, suppose you take some v naught, here. Okay. So then we see that yeah. Okay. So that means let us take this as 0 comma v naught. Okay. Great. Let us take it here. Zero comma v naught. Let us call it q naught. Okay. Then this p of q naught, some v naught. Okay. That means it is here. It is some v naught. Okay. On the other side, if you just look at this generator, and if you look at the mirror image of that generator on the other side, so there will be some generator here. Yeah. Okay. Great. So now what we do, so choose, let us define capital U, which is, here it is the strip, right? The open strip, this one. That means the open strip drawn above. Great. That means you are looking for those coordinates such that the minus pi less than u less than pi. Okay. And therefore, we see that if you take the closure of that, so this will cover that x entirely, right? You are just wrapping up this part. That means you are just taking just okay. So that means here you can take You're just rolling up this strip onto that cylinder. You will get that this strip will entirely cover that cylinder, right? So if you want to restrict that map P to U, so this is nothing but so it is a so this is a parametrization of the cylinder, right? That means it is a coordinate neighborhood of which uh, coordinate neighborhood which covers that x minus a generator. What is that? This is this generator, right? This is a mirror image of that generator. Mirror image of that generator passing through that B naught, right? Because you are omitting these sides of that strip. Okay. So therefore, yeah, good. So therefore, okay. So therefore, if we take V as that x minus, so let us call it that generator as some A, okay? So if you take this and suppose, and this B naught must be in that V, so then we have that P inverse of V. What is that? This is nothing but union of Vn, okay, where Vn is given by these coordinates which are satisfying in general 2n minus 1 pi less than u less than 2n plus 1 pi, right? And this is true. This is true for every n running over 0 plus minus 1 plus minus 2 and so on. And if you look at these Vn's, these are all pairwise disjoint. Okay? And certainly this map, not only it is a continuous map, it is differentiable, right? So therefore, so we see that this P restricted to each Vn must be a homeomorphism from Vn to phi. Okay. So therefore, so if you take any, so if you need to include that generator, so you are going to omit that part, right? And taking the another side. Okay. So if you take any B naught, so that will be covered by some coordinate neighborhood, right? Right. Right. So therefore, so hence this P is going to be a covering map, and that X tilde, that means the plane. This is a covering space of that cylinder. Okay, so this is a very nice example. Another example, so we'll be using this example again in whenever we're getting the stage for determining fundamental group of S1. Okay, we'll see that. So this is number 5, right? So now we have already seen that that R is a covering space of S1, right? Now we'll be witnessing a fact that not only R, suppose you consider the circular helix, right? Which will be given by, so suppose XYZ satisfying that for T belongs to R, X can be given by cosine of T, Y can be given by sine of T, and you are taking Z as some B multiplied with T. Okay. So this is a circular helix with pitch B, right? Okay, great. So, and S1 is, if you want to embed that S1 in R3, so that will be given by using these coordinates. So this will be 1. Okay. Okay. So now it is a very natural kind of map. You can define, that means you are collapsing down the helix to that base circle, right? So that means, so define P from H to X tilde to X by P of XYZ goes to XY0, right? And this is going to be a covering map. Why? Because if you just letting me draw the picture here, so okay. So suppose it is P and this is P star. That means if you take a mirror image along this axis, so this will be the reflection. I'm sorry, this is something like this. Yeah. Okay. So let us take that P star belongs to S1, that is symmetric to P. So, and obviously that map, this P is a continuous surjection, right? This is immediate. By definition, it is true. Okay. So if we let capital U in this way, that it is S1 minus that P star. So that will be an open set in S1, which is equipped with the usual topology that has been induced from R3. Okay. Then we see that. So then we see that. So for that P, you will definitely have a real number, right? So you see that there exists some real number such that phi of cosine of T naught, sine of T naught, and V T naught will be mapped to, let me call it capital P. That would be good. Yeah. Right. Yeah. So this is capital P, right? Now, what we are doing here, so if you just take, so you are just unwrapping that S1 and projecting that to that helix, you will get that kind of thing. Okay. Yeah. So now what we see that if you look at this, so let me define, so what is Vn? So since we have some T naught, so we can be able to define this, that is T naught plus 2n minus 1 pi T naught plus 2n plus 1 pi, right? And this is a subset of R for every n running over is 0 plus minus 1 plus minus 2 and so on. Okay. And if you look at, suppose you take 0. Okay. So that means so what you are getting here, that means you get this curve, this arc, right? From here and this much. Yeah. Okay. This to this. Okay. So for n equal to 0, this, if you take n equal to 1, you will get the other one, this one, up to this. Okay. If you take n equals to minus 1, then you will just move down here and you will get that arc. Okay. And every such part, so these BNs are pairwise disjoint, right? If you look at the picture, it is clear that this part from this one and this is different from this part to this part, right? So these are all pairwise disjoint, and P inverse of open set U, it is the union of Vn. Okay, great. And if you look at the restriction map to each Vn, that means if you look at this arc, if you want to pull down this arc to S1, you will get from that this part up to this one, right? So that means U. So therefore, this is actually a homeomorphism. Great. So hence, this P turns out to be a covering map. And that helix X tilde is a covering space of S1. Okay. Great. So I'm going to give you an exercise here. Can you find out an example which is not a covering map? Well, I'm just giving that. So this is a very nice example actually. So if you restrict your domain space, that means we have already seen that S1, the covering space of S1 is R, right? Now, if you want to restrict the domain space to only positive reals, okay, so then we will find that. So if you consider the map from R plus to S1 defined by, in the same way, e to the power 2 pi I t, so all R belongs to R greater than equal to 0. Then you need to check that this is not a covering map. Okay, this is not a covering map. Okay, but interestingly, it has a very nice kind of feature which is named as local homeomorphism. Okay, what does it mean? That means local homeomorphism. So what does it mean? So that means if you consider a map from some space E to B, it is defined to be a local homeomorphism if each point of, suppose you take some map here, so it is defined to be a local homeomorphism if for each point of E small e of capital E, you must have some neighborhood around that E which is homeomorphic to some open set in B. Okay, so there exists a neighborhood, let us call it V, of E such that P of V P restricted to V to P of V is a homeomorphism, right? Or one can say that this V is homeomorphic to some pattern set in P. So that is what is called a local homeomorphism. Okay, and so example of it can be given by this function. Okay, so the above example, so the above function is an example of this kind of map. And you have seen that if you can be able to prove that this is not a covering map, so that means a local homeomorphism did not be a covering map, right? Okay. So this is a so we can make a note here that a local homeomorphism need not be a covering map in general. Okay. You can have another example if it is possible for you to construct an example from this covering space, that means the helix, the covering space of S1. If you want to restrict that one to some particular domain, okay, so then that will be an example of a local homeomorphism which will not be a covering map, okay, but which one you need to find out. Yeah. Correct. But a local homeomorphism these are all exercises. It is a continuous map. It is an open map. Okay. So these are true. And also the converse part of this note is true. Every covering map is a local homeomorphism. Every covering map must be a local homeomorphism. Okay. Just do it. Okay. So left as an exercise. Okay. Okay. So now let us move to okay.
Can I ask you a quick question?
Yeah. Please.
The map from you said that the map from the non-negative integers to S1 is a local homeomorphism. Shouldn't it be positive, not non-negative?
It should be positive. Yeah.
Okay,
Yeah.
gotcha.
Yeah. Because there will be a problem if you have been looking around that example of that R is a covering space of S1. So if you take any U, any neighborhood, any part of that S1, so you have seen that this is nothing but it is a collection of small intervals, right? So P inverse U will be union of these small intervals, right? Now, if you take a small part of S1, okay, then the inverse image of that small neighborhood will be something like this. But if you take so that means if it is 0, then there is a part here, something like this. Okay, so that will not be homeomorphic to that neighborhood. Okay, that will be embedded on that, but that will not be homeomorphic wholly to that given neighborhood. Okay, so that is why you are requiring it. Yeah. If you're looking around, so if you want to check that, you can just consider any small part of S1, and then you will have this. Okay, great. Another good example, so something one might be interested on, that we have already seen that R is a covering space of S1. We have also proved that circular helix is a covering space of S1. Now it can be proved that S1 itself is a covering space of S1 is a covering space of itself, right? So that means by means of this map, so by the rule, so this P of so let us call it Z. So suppose in particularly you take this function, okay, then it will be a covering map. Why this so? So if you take any particular small part of S1, okay, so usually we always take that part having arguments minus pi by 2 to pi by 2. So if you take that U, okay, so then what will happen? Then this is your so here it is your P. So you are trying to compute this P inverse U, right? So what would be that? So since it is so here Z goes to Z square, so that means if you want to see this map closely, you will find that argument will be doubled, right? So that means this is nothing but this is cos of t sine of t minus pi by 4 less than t less than pi by 4. Am I correct? And then making a round by 2 pi, you will get another one. And so on, right? That means in particular, so yeah, so in general, you can take this Vn as cosine of t sine of t was that 2n pi minus pi by 4 less than t 2n pi. Yes, okay, and this P inverse U, it is union of Vn. Vn's are pairwise disjoint. Okay, and again by using those arguments that has been taken off in case of the usual covering map of from R to S1. So you can prove that this will be a homeomorphism, right? That means particularly Vn is homeomorphic with U via P. So using the same arguments for any other neighborhoods of S1, which will cover up that S1 entirely, you can show that those neighborhoods are also evenly covered by P. Okay? So that means, what does it give you? So this implies P will be a covering map. So in a similar way, you can define the map Z goes to Z to the power n. So that will be again a covering map. Okay? Great. Good. Now, we have already cited an example of a surface which is torus, right? So one can prove that. So what do you mean by a torus? Torus is something, so it is a space that is homeomorphic with S1 cos S1 in the two-dimensional unitary space, right? So that means this T, so actually this is so which can be embedded in R3. Okay. Okay. So which can be embedded in R3. Okay. So that means if you take so this space can be formed using the unit square by identifying its edges, right? So first of all, if you want to so glue that edge, this one and this one, then it will form a tube, right? So this has been glued, yeah, and after using this process, you can take another identification, just identifying these two curves, boundary curves, okay, to get a space, something like this. Okay, great. So this one. Okay, so this is a torus. Okay, and one can prove that actually one can prove that suppose you take a function, prove that this T is homeomorphic with S1 cross S1 with the help of this map. It is a map from that unit square to S1 cross S1, right? Defined by phi of S comma T, it is nothing but this is 2 pi is, we got 2 pi it. Okay, great. And you will see that on that, if you want to apply that drawing, so on those points phi will be equal, coincides. Okay, so that means we define a relation on I cross I by this rule, that is you are identifying 2 points in the square if and only if the functional values are same. Okay, and keeping in mind this relation, you can prove that so this phi is going to be a quotient map. Okay, so that means this is your I cross I from S1 cross S1, and you are going to have some identification space, quotient space, right, which is T, denoted by T. So then you can always, so this is a natural, this is by means of natural projection pi, and this is your phi, and therefore by the universal property of a quotient map, you can always find out a homeomorphism psi from T to S1 cross S1. So this, in this way you can show that this T is nothing but it is S1 cross S1. And so in view of this observation, you have already seen that now by means of the observation, we can show that we can prove that the plane, this is a covering space of torus. Why? So in order to prove this one, you need to prove an exercise. That is, if you have two covering maps, suppose one is from x tilde to x, another one is y tilde to y, so covering maps. Then P cross P dashed will be a covering map from that product space to that product space, x cross y. So this map is this can be defined as, so x tilde y tilde. So this will be okay. So therefore, we have already seen that R is a covering space of S1. Then, so therefore, P cross P from R cross R to S1 cross S1 is a covering map, right? Where P is a usual covering. Usual covering map. Okay? So therefore, so R2 is a covering space of T torus. Great. Now, why we are studying these covering spaces? So, does it have any significant role in determining fundamental groups? The answer is yes. If you look at the example, that familiar example, now let us explore the following fact. I'm just entering into that space, the notion of lifting property of a covering map using this example. Yeah. So we have already seen that R is a covering space of S1, right? Great. So this is a covering space of R is a covering space of S1. Now, if you want to consider a path in S1, suppose you are taking that open semicircle, upper semicircle, okay, this one. So this is a path from, so suppose it is gamma, okay. So gamma is given by this rule, T goes to e to the power pi it, right? Okay. For all T belongs to this. Okay. So then you see that, so this gamma can be lifted to R, where R is a covering space of S1, right? How? Just using this, that if you want to take from, suppose it is a 0 to 1, and this is half. So let us take that as gamma tilde. So let gamma tilde is a path from 0, 1 to R, which is half of T, right? Then you will see that now if you want to, so there is a, so this gamma tilde is a map from 0, 1 to R, and P is a map from R to S1, and gamma is a map from 0, 1 to S1. So that means there is a connection in between these maps. So these diagrams should commute, right? That means you need to have, one will expect that this will happen. And in that case, this is true. Just look at this P composed gamma tilde. What is that? So gamma tilde is t to half of t, and then you are using the p. So this will be e to the power 2 pi I half of t, right? So that means it is e to the power pi I t. So this is your gamma tilde, right? So this is your gamma tilde and this is your p. So therefore p composed gamma tilde is gamma. Okay. Now don't confuse with this one. You can take another one. Suppose just take the other side, lower half plane intersection S1. You will get, suppose we are taking this one. Okay. Then what will happen? So in that case, suppose this is your gamma, then you can define a gamma tilde here. But this will be a path that begins at 0 and ends at minus r. Okay. So that means gamma tilde is a path that can be defined in this way. Okay. Great. Suppose you take, and also this will be satisfying, p compose gamma tilde is gamma. You can check. So that means this is a very nice condition. So you can compute, you can generate that lifting using this relation. How? Suppose you take the path gamma from, so t goes to e to the power 2 pi I t, okay? I'm taking the whole circle for all t belongs to 0, 1. So you need to have some gamma tilde satisfying this property. That means, so need to define gamma tilde which will be satisfying p compose gamma tilde is gamma. So that means, what does it mean? That is, so what is your p? So it is gamma tilde t. This is gamma t. So what is gamma t? This is e to the power 2 pi I t, right? And this is e to the power 2 pi I gamma tilde t. Okay. Then what will be the path here? This is the identity map, right? Now you can do the job using this observation for any path, for any given path in S1. Suppose you take the path which is wrapping the circle twice. Okay, so suppose you take gamma as t goes to e to the power 4 pi I t. Then what will happen? Then your e to the power 2 pi I gamma tilde t should be equal to e to the power 4 pi I t, right? So therefore, this gamma tilde t must be what? Twice t. That means that begins at 0, ends at 2, right? So this number gives you the number of wrapping of that path around that circle. Okay. So this path gamma wraps the circle twice, okay, which is easily viewed by means of this lifting, right? Great. So I'm going to define the lifting of a map just using this observation through this example. Okay? That means given any, so that means suppose you take some space x tilde x. So suppose there is a map from x tilde to x. Okay. And then in general, suppose you take some y, any space. So any map f. So f be any map from y to x. So lifting, suppose it is continuous. So the lifting of a continuous map f from y to x is nothing but a continuous map f tilde from y to x tilde, right? Satisfying that the diagram commits, that is P compose f tilde should be f. Right? So this is your f tilde. So this is how one can define a lifting of a continuous map from any space y to x. Okay? With the help of a map from continuous map from x tilde to x, which is P. Okay, so this is true. So we will see that. So we are concentrating ourselves to liftings in covering spaces. Okay? And that will help us extensively to characterize the fundamental groups of certain spaces. Okay, and we will see that suppose a covering space is given, then we will see that paths can be lifted, as well as if you take path homotopes, so these also can be lifted in covering spaces. Okay. So it's a very nice kind of feature that a covering space of some space bears. Okay, so so what will be the picture? So to get the flavor, I need to draw the picture here. So suppose this is your x, and this is your x tilde, and there is a covering map which is P. Okay, satisfying that, if you take some E naught here, that E naught will be mapped to some P naught. Okay. Now what is happening here? So suppose you take a path. Okay, gamma. Okay, so this is your path gamma starting at B naught. Then you can assert that there has to be a unique lifting to that path gamma in the covering space of x tilde, which will be starting at E naught. Okay, so that means there is a unique lifting gamma tilde in the covering space of x that begins at E naught. Okay, so this is a very nice theorem, and I think you have got that point, right? So given any path in X starting at B naught, there must be a unique lifting in the covering space of X that begins at E naught. Okay. Great. So how do you define this lifting? This is a very nice theorem, and you need to take care of a bit here because this is not a very easy job to construct such liftings. But we are using simply compactness of this closed interval. Yeah. And another property that it bears that that is connectedness. Okay. Great. So you know that in a covering space you can always have a Lebesgue number delta, right? That means given any covering, finite covering of that covering space, you take any set having diameter less than delta that can be embedded in some open set that belongs to that covering. Okay. So using that property, you can always construct. So I'm just so suppose since I'm just giving you a sketch of that. So since P is a covering map, then you can always construct an open cover of X, right? So then that X can be covered by some U alphas, where all these U alphas are evenly covered by that P, right? Now you are going to take the inverse image of each of these U alphas via this gamma. That means gamma inverse U alpha. So that is going to be open set in that closed interval, right? So that means F inverse U alpha, gamma inverse U alpha will constitute an open cover for that closed interval, but that closed interval is compact, so you are having a finite number of cells, right? So ultimately, so eventually one will get a partition of suppose let us call it so 0 S0 S1 Sn 1 equals to 1. So one will get a partition of this kind, satisfying that if you take any subinterval, that gamma of that subinterval will be mapped into some U alpha. Let us call it Ui. Okay. And this is true for each I runs over 0, 1, 2, n minus 1. Okay. This can be given as an exercise also. Okay. Exercise. Good. Just using the property of Lebesgue number, the compact space, you can always put this. Okay. Great. Now, after having this partition, so let us first start from, I'm just going to, okay. That means suppose this one. This is your 0 to 1 interval. And you have already inserted some subdivisional points here. But I will be magnifying one particular subinterval, which is the first one, that means S0 to S1. Okay, the others are in this way, given by this way. Yeah, this is your Sn. Okay, now since the path is given here, is gamma. So what we are doing here, so this is your B naught. Okay, this is your B naught. So you are considering the open set U naught, right? Because here gamma of S naught comma S1 is a subset of U naught, right? By that statement. Okay? Good. So therefore, so using this B naught, so this is actually, so this B naught is gamma 0, that means gamma S naught. Okay. Now we are going to take the inverse image of this point, gamma S naught, which is B naught, right? That means it is P inverse B naught. And recall that this P inverse B naught is a discrete space and it will intersect each slice exactly once, right? So therefore, you can take, so this P inverse B naught intersect V beta. What is V beta? V beta is this one. This P inverse U naught can be written as union of V betas, where V betas are slices of that U naught in the covering space using that P. Okay. So P inverse B naught intersection V beta. So that is going to be a point. Okay. So let us take that. So let us call it E naught. Okay. That means, suppose this is your U naught, and you are having some, this is your covering space, X tilde. Okay. So that means okay. So suppose it is your E naught. Here. Okay. So E naught is P inverse B naught. That means P inverse F, P inverse gamma S naught. Okay. Correct. And we call, so suppose, so this is your B beta. Let us assume that denoted by V naught. Okay. So let us denote that V beta as V naught. Okay. Now I am defining, so we are assuming that the lifting of that gamma is supposed to satisfy this property that gamma tilde of S naught, because we have already seen the definition of a lifting. That means that might be a path which starts at gamma tilde S naught, right? So that means gamma tilde S naught should be E naught. Okay. So this is gamma tilde 0. So we are assuming that gamma tilde is not, must be E naught. Okay. Now, another property that it needs to satisfy, which is that this gamma tilde ought to satisfy that the diagram commutes, right? That means P compose gamma tilde should be comma. So that is, what does it say? Gamma tilde of, so if you take that small part of this subinterval, so that will be mapped under this gamma tilde, where, so it will be mapped, it will be a subset of P inverse of gamma of S naught S1. That means it is a subset of P inverse of U naught. And what is that? This is union of V betas. Okay. So that means this gamma tilde of that closed interval S0 to S1 must be a part of V betas. But here, connectedness of that interval S0 to S1 will be playing some role, right? Because this E0 belongs to that V0, okay? And this gamma tilde needs to be continuous, right? So it should map a connected set, this one, to a connected set in the covering space. But we have already seen that this is nothing but this is a subset of union of V betas. So that means that must be part of some V betas. But here, since connectedness is involved and E0 belongs to V0, and what is E0? That has been assumed to be gamma tilde of S0. So that means this implies, since these V betas are slices, that means they are pairwise disjoint. So therefore, this gamma tilde of this particular subinterval will be embedded in V0 completely, right? So therefore, if you are taking any point here, suppose you take in S, small s, so this small s will be mapped to this gamma s, okay? And this gamma s will be carried forward to that slice V0 via the inverse map P inverse restricted to V0. That means you are getting some point here, which is P restricted to V0 inverse gamma s. So that will be defined as gamma tilde s. Okay. So that means this. So this is your gamma tilde for that subinterval. Okay. So we define gamma tilde of S as P of this gamma S for all S belongs to this subinterval. And we are doing the same thing for others also. And this gamma tilde, this is certainly a composition of two continuous maps, right? One is P, another one is another one is this one. P restricted to V naught inverse. So this is a homeomorphism, right? So therefore it is continuous. So this is so gamma tilde is a composition of two continuous maps. So therefore it is continuous. Okay. So this is a well-defined map. This is continuous map. So now we need to proceed for other subintervals. So we will jump at the next one, right? That means from S1 to S2. And again, using the same arguments, because note that gamma of this part is again in some U1, right? For U1 is evenly covered by disjoint, let us call it W betas. Okay. And then again, this S1, so this gamma tilde S1, right? This has already been defined above by this map, right? So this gamma tilde S1 should be in some predetermined set W betas. Okay. So must be in some W beta. Say, let us call it W1. So along the same line as above, we can define that map over S1 to S2 by means of this slice W1 and taking the restriction of that covering map on this over this W1. So that will be a homeomorphism. So therefore we are taking this P restricted to W1 inverse of commas. Okay. So continuing this process using the compactness and using the connectedness here, you can easily define a finite series of maps. Now the Pesting lemma will come into the picture. Okay. So using Pesting lemma, you can say that ultimately that the gamma tilde that can be defined on each subintervals, so will be a map from the whole interval 0, 1 to the covering space of X, and that will be a continuous map by using Pesting lemma. So will be a continuous map by using Pesting lemma, right? Great. Great. So that will be satisfying. That gamma tilde P compose gamma tilde is gamma, and gamma tilde will begin at, by definition, E naught. Okay. So that means in the picture, this is going to be, so suppose this is your, sorry. So one minute. And that will be, sorry. Yeah. Right. Okay. Okay. So that gives you a lifting off. So this is a lifting of gamma. to the covering space. X tilde of X. Now, is it unique? The answer is yes. But for that one, I'm just giving you another exercise. Just using the connectedness. That is, if you have two liftings, suppose one is gamma tilde, another one is gamma tilde test. Be two liftings. Let us give you the general problem. I'm not taking parts. We can see that. So if you take two continuous maps, two liftings of a continuous map, be two liftings of a continuous map f from y to x, where p from x tilde to x be a covering map. Okay. Also, let me give you just local homeomorphism, be a local homomorphism. Yeah. Okay. Such that for some point x naught belongs to x, sorry, for some y naught belongs to y, f tilde of y naught coincides with f tilde dash to y naught. Okay, then you need to show that these two maps will be identical. Okay, provided we need to use that this x should be a connected T2 space, right? So this provided x is assumed to be a connected T2 space. So if it coincides at some point, it will coincide entirely. Okay. Just using the connectedness and T2ness, you will get that result. And using this one, because every covering map is a local homeomorphism, so using this, you can say that, so in view of this, one will have that the defined gamma tilde is the unique lifting of gamma in x tilde that begins at e naught. Okay, so that is a very nice. You should always careful about that. That begins at e naught. So that has been specified. That means if you take another e naught dashed from b inverse b naught, so you will get another lifting. But that is unique. That is a unique lifting of gamma that begins at e naught dashed. Okay. So this is a very important note, right? So that is important. So where it starts, it should be specified. Then it is unique. Okay. Great. So I'm just finishing my today's lecture, just giving you a general definition here for a continuous map. So suppose P be a continuous map. Let me to X be a continuous map. Okay. Then this P is defined to satisfy path lifting property, is defined to have path lifting property if for any specified point E naught belongs to X tilde, and for a given path gamma from gamma in X such that gamma naught is P of E naught. Okay, let us call it B naught in X. Then there must exist a lift gamma tilde from 0, 1 to X tilde of gamma such that gamma tilde of 0 must be E naught. That means that lift will start from E naught and the diagram commutes. That means P composed gamma tilde must be gamma. Then this kind of map will be said to have path lifting property. Okay. That means we are going to set our goal to prove that any covering map will have path lifting property. Okay. Good. So with this one, I would like to stop. So any question?
Could you go back? Could you scroll up a little bit? Let's see.
Which one?
A little more. Okay, yeah, right there. Yeah, about the uniqueness of the liftings. Let me see here. Yeah, should it be Y is connected in T2, not X?
1 minute. Yes. Okay. Why should yes. Okay. Yeah. Thanks.
Okay, thanks. Just making
sure.
Yeah.
Sorry. That should be Y. Yes. Thanks a lot. Because that unit interval is connected on T2. Yes. Thanks. Okay. Any other question? So if not, we can leave it, right? Okay. Thanks.